Hi everyone, good day. Thank you for joining today's training section. My name is Aaron Huang. I'm a motor drive engineer and also work on firmware development. Please feel free to ask questions at any time during this session. Okay, today we'll walk you through technical training. Let's divide it into 4 main parts. This section is designed for both internal engineers and our customer side engineers to better understand and use our motor drive solution. Okay, part 1, basic theory. We will start with some basic theory to build a common understanding. This includes an introduction to permanent magnet synchronous motors, or we call it PNSM, more commonly referred to as BLDC motors. We will also briefly cover the concept of multiple loop control systems, which are essential for stable and efficient motor operation. Okay, second part. The second part is the most important section of today's training of motor tuning GUI. Okay, we will spend more time here because this is the main tool you will use when tuning the motor. We will walk through how to connect to the GUI. We can use what each parameter means and how to fine-tune the motor performance in real time. Okay, and part 3 is we will introduce the evaluation board, and the last part is monitor. We will talk about its debugging tool. Debugging tool is a C scope. Here is a block diagram of a PNSM speed control system. Okay, we are using beta control, which is also known as indirect field oriented control, or simply FOC. So we will call this system by FOC in this session. This system includes, you can see this photo, a speed control loop and a current control loop, and DQSS coordinate transformation, which is a key to decoupling torque and flux. And here, an SVP block. SVP block is a space vector pulse with maturation. It used to generating precise voltage vectors to inverter. Okay, and it is also include a rotor position estimator, which provides the estimated angle for coordinate transformation. Okay, and finally, the chip control the inverter to drive this motor, and we also need the current some information from the motor, like V-bus voltage or the phase current. So we can use the hardware, the shunt resistor, to get a phase current information. Okay, now let's take a look at the mathematical model of the PNSM. Okay, first let's talk about the coordinate transformation. Okay, we need to simply this control, so we use coordinate transform to cover the original three-phase ABC three-phase system into a DQ rotating reference frame. In this frame, we can treat torque and flux as decoupling components, which makes the control easier and more precise. Now let's focus on equation 1. Okay, equation 1, you can see the dynamic voltage equation in the DQ frame. Okay, so on the left, VQS and VDS are the voltage in the QSS and DSS. They are determined by motor's resistance at RS. You can see here RS and the inductance LQS and DS, and the phase current IQS and IDS. Okay, we also have this term omega E and lambda F, which represents the back EMF from the rotor's magnetic field. Okay, and the torque equation, we can check this equation, equation 2. We have the electromagnetic torque equation. It shows that the torque TE here is proportional to the interaction between the rotor magnetic flux lambda F and the stator current. This is for a fundamental basis for FOC. So I can give a tip. In the simple terms, QS's current generates torque, and the DSS current controls flux. Okay. This slide continue from the previous slide. Let's look at how we simply the motor model and how it helps us design the control. If we reset the DS current to 0, and as the equation 3, so the torque becomes directly proportional to the QSS. So in this equation, we just can see IQS. We don't see any IDS information in this equation. And the constant KT is the torque constant of the motor. So this is a common assumption in FOC. We let the permanent magnet flux align with the DSS, and we only use this IQ to control torque. So TE equal to KT product IQS. Okay, and the next equation is like equation 4. Equation 4 shows the mechanical equation of the motor after the load is implied. Here I describe this equation. T is torque, and the Jm is the motor's moment of inertia. Bm is a damping of friction coefficient. TL is the external road torque, and omega R is rotor speed. Okay, let's summarize this slide. Okay, by setting IDS equal to 0, we simply the torque model like this block diagram, and build a control system to act very much like a traditional DC motor, but with higher efficiency and no brushes. Okay, let's talk about the coordinate system. On this slide, we show the relationship between 3 different coordinate systems that are essential in motor control. First, the 3-phase stationary coordinate system here. We can see the A, B, C is a ABC frame. This is where the original motor voltages and the current exist. Sinusoidal waveforms that are 120 degrees apart. Okay, next, we have the 2-axis stationary coordinate system. We call it alpha and beta, the red line. Which line is a fixed reference frame. This is simplifies the mathematical handling of the motor signals. And finally, we rotate to this alpha beta to DQ frame. DQ frame, we call it a synchronous rotating coordinate system. In this frame, we can see this is a motor, and gray part is a stator, and the blue part is magnet. Okay, so in this frame, DSS align with the rotor magnetic field here, and the QS is uh, perpendicular to uh, magnet is a QSS. So this is extremely useful because it allows us to decouple the torque and the flux. So we can imagine that DSS ID is control the flux and the QSS to control the motor torque. So we can similar to how we control a DC motor. Okay. This slide let's divide it deeper into multi-loop control architecture, as illustrated in this diagram. This structure is critical for optimize motor drive performance, and it integrates three key components. We call it. There are three loops. Blue block is current loop, and orange is here observer, and the green part is speed loop. Okay, and the speed loop highlighted in green, so continues to regulate the motor's speed. Okay, and let's move into the current loop. Um, Current loop, this is a inner loop focuses on precise current generation, IQ and ID. Okay, and we also measure phase current from motor, and we get the current information to do a closed loop control. Okay, and observer. Okay, because this is a sensorless FOC system, so the observer shown in green. Okay, it enhances system accuracy by estimating critical parameters. It pos it process the measured current here, I alpha and I beta, uh, and along with voltage feedback, and V alpha and V beta is a voltage command to calculate use sensorless algorithm to calculate the motor position east theta and the motor speed east speed. Okay. And so the observer provides reliable feedback to both loop, current loop and speed loop. Okay, so the overview process is here. First, we just mentioned that ABC friend transfer to ABC friend transfer to alpha beta, or alpha beta transfer to ABC friend. We usually use Clark transform or inverse Clark transform. And the second, the alpha beta frame transfer to DQ frame by Park transform or inverse Park transform. So this is the foundation of FOC. Okay, building on our previous discussion of the multi-loop control architecture, let's now take a closer look at the speed and the current loops in action, as shown in this diagram. Okay, first we talk about the speed loop. The speed loop is here, a red box. Let's focus on it. And the speed controller adjusts the torque command here, adjust torque command IQ to achieve the desired speed, and it compares the reference speed omega r. This omega r is from speed estimator scheme. Okay, and okay, and the different and we use the speed difference and through a PI controller. Here is speed controller. We usually use PI controller to generate the desired current IQ to control the torque. And let's talk about the current loop. First, we talk about IQ current loop. In the DQ frame of PNSM motor, IQ is the Q axis current that generate torques. We mentioned that, and and IQ commands it means setting torque. So IQ command is desire here. Is desire Q axis current set by the speed controller output to achieve the target speed, and it acts as the torque command. And the higher IQ command means more torque to meet speed demands. Okay, and because we have to do closed loop, so IQ feedback here. IQ feedback it means actual torque. So the torque IQ feedback is the measured Q axis current reflecting the motor's actual torque, since torque is proportional to IQ. So the current controller adjusts voltage to match IQ with IQ command. So here is a current controller. So this current controller, we usually use PI controller to control this current, and uh, uh, and we generate VQ uh, to uh, to generate a PWM signal to control inverter. Okay, let's summarize this slide. So IQ control enables precise torque regulation, allows the motor to respond dynamically to speed and load changes. Okay, let's talk about the current loop second part. Uh, IQ control basis. The ID axis current in the DQ frame affects magnetic flux, and they usually control to zero for max torque, but can be controlled for specific need. Here, ID usually control to zero. Okay, and we talk a lot of a concept, decoupling control. So the current control adjusts voltage to decouple ID and IQ effects. Ensure IQ controls torque independently of flux changes. Okay, but ID we also can do another function, like a weak magnetic control. So ID also can enable weak magnetic control with negative current here. So if we set the negative command, we can use the flux weakening function. Okay, and weak magnetic control can extending speed range beyond the base levels. Okay, so in short, ID handles decoupling and weak magnetic control, pairing with IQ for full control. Okay, and let's explore the specs better pulse width modulation (SVP-DIN) strategy. As shown in this diagram, which is a key to driving motor voltage. Let's talk about SVP-DIN basis. SVP-DIN use 8 switch patterns from 6 IGBT here, or 6 MOSFETs. Okay, inverter to the motor voltage vector. So this is a vector with one of 6 sectors here. we usually has 6 setters in SVP-WN strategy. So so the vector falls within one of 6 sector, like S3, S1, 5, 4, S6, S2, and is synchronized from the 2 basic voltage coordinate. Okay. So this method ensures efficient voltage control, optimizing motor performance by aligning the output with required this torque and speed commands. Later on, I will introduce the advantages of using SVP-N strategy. Okay. First part, we finished the first part, basic theory. So now let's move into part 2, motor tuning GUI. Okay. The motor tuning GUI is a user-friendly interface that simplifies parameter adjustment and performance testing. It allows engineers to visualize real-time data, tune control loops, and validate setting efficiently. Okay. And second, the motor tuning process. The motor tuning process involves initialize the system. So, so we will starting baseline values that use the GUI to adjust speed and current loops. Okay. And we also talk about the FOC workflow. The FOC workflow operates as a state machine. This is a very important concept in FOC control domain. Okay, and in summarize, the motor tuning GUI streamline the tuning process of FOC enhances control accurately. So proper parameters setting drive success. Let's dive into the hands-on example next. Okay, this is a motor tuning process. And let's walk through the motor tuning process in the correct sequence as shown in this flow chart to optimize motor performance. Okay, so first we have to open the motor tuning GUI, this step. And second step, load parameters. We load the motor parameters into the GUI, such as resistance or inductance or some parameters to establish the starting point for tuning. Okay, and the third steps, motor tuning. We input some parameters to fine-tune this system and adjusting some parameters like PI games to optimize speed and torque control. After motor tuning, we export a header file. Okay, we export the header file to here, KLC NDK. KLC NDK is a firmware platform to development on Cortex M0 system. Okay, and after export header file, we compile this project, and we program to NCU, and then we test the system motor test. Okay, and this is a sequence. So after motor test, loop back to tuning. So based on the test result, we loop back to motor tuning and repeating the cycle: tuning, export, and compiler, programming, motor test. This is a loop. So until we test it and fine tune this system until optimal performance is achieved. Okay. Okay, and let's explore the open loop run up workflow. Uh, okay, a state machine designed for fan motor control, shown in this diagram. A state machine, I have to highlight this slide. State machines play a crucial role in FOC control schemes. So before we fine-tune a system, we have to understand the state machine in in this system. So the state machine initially says in the standby state. Here, standby state. Okay. Upon receive a user command here, start up command in orange box. Okay. And it transits to detect DET. This state. Detect it means detection state to determine the motor current status. And whether is rotating forward or rotating in reverse or at a standstill. There are three conditions in this state machine. Okay, if the motor here is stop, okay, we enter the pre-charge state. Pre-charge state to pre-charge the boost circuit, and then proceeds to the align state to align the rotor to a known position, and followed by ramp state. Ramp state, we usually call it open loop state startup or synchronous startup. Once the target speed is retrieved, the system moves into the run state. Run state is closed loop operation. Uh, the closed loop operation, it means we speed closed loop and the current closed loop and position closed loop. Okay, so this is startup sequence. Okay, next, let's talk about the second scenario. Okay, here is forward rotation. Forward station, because there are some condition, we need to use this. We need to have this function. Okay, forward wind start if the motor is detected to be rotating forward, so it will transition directly to the long trans state. Long trans state for temporary control, stabilization, and then enter the wrong state. Okay, and then the third scenario here is more complicated. Okay, this is third scenario, reverse wind condition. Okay, reverse wind condition, it means the motor is spinning in the opposite direction. And conceptually, it needs to be stopped first before restarting in the correct direction. And two braking modes are available. First is reverse function and brake function, and which will be explained later. And after braking, the system the system goes to the stop state. Okay, and restart the motor. Okay, and additionally, if the system error is detected here, the system enters the stop state as part of its mm, protection mechanism to halt motor operation. And when the start command is received, here, start command is received, the motor transitions to soft stop to stop smoothly. Okay, this slide, we talk about the second startup algorithm. Let's now explain the adaptive run-up workflow for fan motors, as shown in this diagram, which builds on the previous open loop workflow. So the workflow is very similar to previous workflow. Okay. And state machine overview, this state machine uh, tailored for fan control, we process the align and the ramp states with here adaptive ramp state, offering a more dynamic startup process while retaining other status. And okay, adaptive run up feature here. Uh, Unlike the previous workflows align and run up, adaptive ramp dynamically adjusts the saturation based on. So it can provide a smoother and more efficient startup for fan application. So this table you can see the state machine state name and the description. In the information box below, useful details are displayed based on the input. So this is the motor tuning GUI. This is a tool, and let me check it. Okay. So there are some features and tab on it, like load parameters and save as parameters and export header file and save as header file and the information tab about. And this area is adjust parameters area. We can users can input some parameters on this area, like function, motor, hardware, etc. And the information area in button area, it shows some very important information to user, like maximum current and maximum voltage and the maximum duty output.
This slide compares the two versions of our motor tuning GUI, simplified and complete. The simplified version, with only 28 parameters, is designed for beginners. It keeps things minimal so that users can quickly get the motor running without dealing with too many settings. On the other hand, the complete version provides access to all 93 parameters. This is intended for advanced users who want full control over every aspect of the motor tuning process. The tables below illustrate the difference. The simplified interface shows only the essential parameters, while the complete interface enables every parameters page for detailed tuning. The slide shows how to switch between simplified and complete modes in the motor tuning GUI. First, go to the About section in the software. In the pop-up window, you'll find the Simplified Mode checkbox. When the box is checked, the software runs in simplified mode with fewer parameters. When it is unchecked, you will have access to the complete version with all parameter interfaces enabled.
Okay. So how to start a motor tuning process? Okay, first we have to load parameters. The file is in Excel format here, and contains all required setting and parameters in this file. Okay. And after tuning this, after fine tune this system, uh, we have to export header file. So clicking the export header file, and export the header file is in the name of here. We look at this header file. The name is fixed. The name is MC parameter M0 .h. And this file should be included after tuning. After export, this file should be included in and compiled with the KLC project. Okay, there is very important tip. Okay, the first time you click export header file here, uh, you need to choose a save path like this. It's a fixed path. And you need to choose a save path. This path will then be locked and used for all feature exports until you restart the GUI. So please remember it. Okay. In the following sessions, we will provide a detailed explanation of these parameters to begin. And first, we have divided it into 4 key blocks, such as basic and start up and stop. And the next part is duration-aware motor stop. And the next part is control loop. Okay, so I will talk about each block's parameters in the upcoming details. Okay, let's start with basic block of the motor tuning GUI. This session includes the following key components, such as function and the motor. HW means hardware and user and the RAM. Okay, let's go back to the tuning window. In the basic function, there are 2 start up mode user can choose. First is synchronous ramp. It's open loop start up. And the second choice and the second mode is adaptive ramp. Okay, adaptive ramp we also call it adaptive stop. Okay, and the observer mode. But now we just provide one observer. It's based on back ENF method observer. And we also provide 2 kind of SVN mode. Is 5-segment SVN and 7-segment SVN. I will discuss more advantages of 5-segment and the 7-segment SVN strategy. Okay, this page compares several PWM modulation techniques, including SPWM. SPWM, the name is sinusoidal pulse width modulation. This is a traditional and basic PWM modulation. And it also include 5-segment SVPWM and the 7-segment SVPWM. In this table, I've compared key metrics such as here, DC voltage utilization and switching loads and total harmonic distortion. We usually call it short as THD. Okay, and mm, okay. First, we let's talk about the 5-segment SVP diagram. Uh, the advantage is lower switching loss. But the disadvantage is a slightly higher harmonic distortion compared to 7-segment SVP-N and SP-M. Okay, and because the THD performance is not very is the harmonic distortion is higher, so it may be produce more uh, acoustic noise in certain motor applications. But we can see this is a very important advantage is DC voltage utilization. Okay, it's about 86.6%, and the traditional SPWM strategy is just about 78.5%. Okay, a higher DC voltage unit utilization means we can achieve higher motor speed. Okay, and the 7-segment SVPWM, it also provide higher voltage utilization, about 86.6%. But the disadvantage is the switching loss is higher. Uh, and the switching loss is higher than 5-segment SVPWM. Okay, but the advantage is lowest uh, this strategy provide lowest and the minima THD. So uh, so this control, how can I say that? It also okay more balance. There is a very good advantage is a more balanced switching pattern, and it can reduce common mode voltage. Okay, and because the THD is lower, so it means we can get a quieter motor operation. Okay, on this slide, we are comparing the waveform of 5-segment and the 7-segment SVP diagram. You can see both phase current, the green line is phase current, and phase voltage in yellow waveform. The difference in phase current isn't very obvious. I think the current it seems very similar. But the phase voltage clearly shows how the switching patterns differ between the two methods. It's very different. This is a 5-segment SVP diagram, and this waveform is 7-segment SVP diagram. Okay, and one thing to highlight about the 5-segment approach is that there is 120-degree interval here in every electrical cycle. So where there is no switching activity. So this helps to reduce switching losses, which can improve efficiency in certain applications. Okay, next page. This page is the motor section within the basic setting. Here you need to input some fundamental motor parameters. Uh, because this motor system is sensorless FOC system, so we need to input some motor parameters like this diagram. This is a motor, so we have to input motor pole pairs, and this motor's maximum speed and the duration is also very important. And in this blue box is a motor model. So we have to input R. This R is the phase resistance, and the LT is DSS inductance, and the LQ is QSS inductance. Okay, we can see these tips. Sometimes you can find the LD is LD doesn't equal to LQ because IPNSM has a silence structure, so the two value is not the same. Okay. Okay. This page is about basic hardware, HW, and the HW is hardware. So uh, hardware section which introduce various parameters related to hardware and the NCU. So I will explain this using the diagram on the next page. It's easier to understand the parameters. Okay. So let's see the green cells. It presents input fields where users can enter or adjust parameters. So the diagram shows basic motor drive architecture, including here six switches like IGBT or MOSFETs, and a DC bus capacitor, and a current sampling circuit, and OPA operational amplifier for current amplification. Okay, and voltage sensing here. Okay, so hardware section is a very crucial. So we have to before fine tune this motor, uh, correctly inputting the parameters is very crucial, like current sensing shunt resistor, because it provide is connecting to a protection. So a shunt is very important. Okay, and we also have to input the PWM frequency and the time. Okay, like and amplify gain and the ADC reference voltage and the V bar scan. Okay, so this page is not difficult to input because you just follow the system design to input the parameters. It's okay. Okay, this page explains the details of how the parameters are calculated. So you can refer to this explanation here. So we won't go into details on it now. So after this training course, you can check the equation by yourself. The basic okay, this page is a user page. Is for setting the maxima and the minima values of the command input, as well as the acceleration time from the maxima to the minima to maxima command. So let's see this diagram. Okay, the vertical axis represents speed, and the horizontal axis represents the input voltage. It's a VSP command. VSP command is a input voltage level. Okay, so in this diagram, it illustrates the relationship between the input voltage, and the resulting speed command. Okay. So we have to input a few parameters in here. So first, you need to define 3 voltage thresholds in the program on the KLC NTK platform. The three parameters, VS VSP stop voltage and VSP start voltage and the maxima voltage. These settings are shown in blue box in the diagram. And a small hysteresis is added between the stop and the start voltage to avoid chatting and bouncing when the signal is near the threshold. Okay. Okay. Let's talk about potentials. Uh, potentials is we also have to highlight this session, this part. Potential play a very crucial role in the system architecture. First, they help prevent hardware damage. Second, they act as a safeguard in case of algorithm failure. In addition, potential features assist designers during debugging by quickly pointing out potential issues. There is a tip. If you run into any problems while using this system, feel free to reach out to your FAE or AE engineer. Uh, and the tip is here, and don't forget to include the error code to help speed up the diagnosis. So there are some different potential error code and error name and description. And like OCP, OCP is firmware base current over voltage, and the offset fault is current sense bias over offset voltage failure, and OVP is over voltage and under voltage, and low sync and over speed is used to observer. Okay, observer rows of synchronization and observer speed estimation error. And the less error is ramp over time. Okay, so we will talk more details as following. Okay, so this is a round window. So there are some parameters has to input. Okay, so the previous page introduced some potential functions. On the basic around page, you can input specific parameters like over voltage, or over current level, or over current times, like over speed time, etc. Okay. This page explains the relationship between over voltage potential and over voltage potential and under voltage potential, as well as under oh, at the same time we have recovery, or we call it release function. Okay, so please refer to the diagram to the right here. In this chart, the vertical axis is V bars, it's bus voltage, and the horizontal axis is time here. Okay, and during the OVP, over voltage potential, this part, and the UVP, under voltage potential. Okay, this period, the motor runs freely, and it's free run, like this line, this area is free run, and in the other intervals, the motor is actively driven here, because the voltage is lower OVP level, so it's the motor is driving. Okay. Okay, let's talk about run up time out. Okay. This slide is plan the run up time load potential. Here, as you can see in this figure. Okay. Uh, in the active RAM state, if the motor stalls and cannot stop, like this area, okay, the controller continues to output current at the minimum frequency. Okay, if the stale lasts beyond the timeout this time, okay, the potential is triggered. Okay, so you have to set this timeout value uh, here. The typical value is 5,000 milliseconds. Okay, okay. Let's talk about overspeed. Since our control method uses a sensorless algorithm, so when the algorithm fails, the calculated speed may exist or fail below uh, the reasonable speed range. So here, over speed area is the speed is too high, and here the over speed area the speed is very low. So we can define this area is unreasonable speed range. Okay, so as shown in this diagram, when the estimated speed enters to the over speed area and remains there longer than this setting over speed time, okay, the potential is trigger the over speed potential. Okay, okay, we finished the basic part. And the next, we will move on to the motor tuning GUI start up and the stop section. This part is mainly divided into several key areas, such as pre-charge. We mentioned those state machine uh, in the previous slides, like pre-charge, alignment. Alignment is also called align, and the ramp, ramp up, and the adaptive ramp, and the soft stop. Okay, let's start by looking at the current waveform to demonstrate the traditional startup method. This waveform is a very traditional and startup method. Okay. Uh, Startup method one, we as known as open loop drag or synchronous motor stop. Uh, so first, the step is step zero is pre-charge. But pre-charge we cannot see the waveform on this waveform. And next step one, is alignment. Is two steps alignment. Okay, and followed by, oh, this is a line, and followed by an open loop ramp up. This area is ramp up. Okay, and when the target speed is hit, it switches to closed loop control, both alignment here, alignment and ramp up. Okay, we in this system we use constant current control, so you can see the current is constant current command to ramp up. Okay, so now we have to discuss the parameters in this slide. So we'll use this chart to show how the state machine relates to the parameters. Okay, so the ones inside the green box are parameters. Here, the green box is parameters, and you can input the parameters in parameters window. Okay, so let's discuss this diagram. The vertical axis represent the speed command here, motor speed, and the horizontal axis represent time. Okay, in the first step, we just mentioned that in the previous waveform. First, first pre-charge. In pre-charge state, you can input two parameters, duty cycle and the time. Next, during line 1 and line 2, you can set the duration and the current command and the current run up time. Then, in open loop startup, we call it ramp. In the ramp state, you can use input here current command and the run up time and a very important parameter here, like this value, speed target. Okay, which is the speed point to switch into closed loop. Closed loop. So this this parameter is very important. Okay, and after ramp, uh, the state switches to speed loop. So speed loop is a closed loop control. The state machine, we call it wrong state. Okay. Next, let's talk about the second startup method. The startup method is adaptive ramp. Okay. In this method, the the adaptive ramp state it has some advantages. Okay, like quickly transitions into closed loop within just a few electrical cycles. So uh, let's see this waveform. Uh, in adaptive ramp state, here it's just one electrical cycle and switches to closed loop. It's very fast and smooth. So uh, in Chi in Chinese market, uh, this method is widely used in fan applications because it offers fast startup and a smooth user experience. So, but the trade-off is that it needs some parameters tuning to work well. Okay, we also use this flow chart to describe the state and parameters. This state machine of four adaptive ramp is quite similar to the uh, startup method in open loop ramp up. There is a different state here, adaptive ramp. Typically alignment here. Typically alignment is not required when using adaptive ramp. So we don't use a line function in this startup method. But if you want, you also can turn on a line function. Okay. Okay. In the next page, we will talk about more details about the parameters. Okay. That we covered the parameters for both startup methods. So let's see where to input them in the GUI. So first, the pre-charge state. You can see two parameters in this window. Time, pre-charge time, and the duty, the pre-charge duty cycle. And here we also in this GUI, we also provide some typical suggestion in this tool. Okay, and the second is alignment. We already discussed these parameters in previous page. So there are 5 parameters have to input. Okay, so this page is ramp. Okay. Uh, okay, here I want to highlight the importance of the speed target parameter. It determines the speed at which the system switches to closed loop control. Since we are using a sensorless algorithm based on backend F, so the motor needs to reach a certain speed for the backend signal to be strong enough for reliable control. So the typical value shown in the GUI here, uh, uh, you can use as a reference here, typical value. Usually, this value is set to around 5 to 10% of the maximum operation speed of motor. Okay, this page is for start up and stop. For the parameters in adaptive ramp mode, it's recommended to start with the typical value like this, typical value. Uh, However, user have to tune the current command because um, current command needs to be adjusted by the user as it depends on the motor load. Yes, this value it depends on the load. So in general, the required startup current is proportional to load uh, on the motor. Okay, and this page is for soft stop. Uh, Next, let me explain the soft stop function. This is a handling process before stopping the motor. Okay, let's describe why we need to use soft stop. If the PDAN signal is suddenly turned off while the motor is running, the abrupt change in current may cause mechanical noise. Uh, to avoid this, when a stop command is received, the controller sets both the ID and the IQ here, this command, to 0. Uh, this allow uh, this allows the motor speed to decrease naturally, and the controller will exist the soft stop state under one of two conditions. Okay, so the two conditions is the timeout here, timeout, and the speed threshold. Okay, also the controller will insist the soft stop stay under a timeout is reached, or the step drops below the predefined threshold. Okay. Once either conditions is met, the PDAN output is turned off immediately. So let's check out the waveform. We just talked about the soft stop function. So uh, uh, when receiving a stop command, we the system goes to soft stop state. So you can see the first current is limited to very small. Okay, and it remains few seconds or a few milliseconds. Okay, so we also talk about the tailwind stop. Okay, let's check out the tailwind stop waveform here. Uh, this line is a phase current. So let me talk the motor start up line here. Okay. This first part, the motor is running and the gas turned off. So after the motor stop, we turn on the motor again. So in second part, first the motor starts up a line, and in first check which way is spinning and what speeds it's at. So here is a motor state check. Okay. is we just mentioned that in previous flow chart. So this is detention state. We we have to know motor is running at forward or reverse or stop. Okay. So in this case, uh, this motor, this is a tailwind stop. So uh, it smoothly switches into closed loop here. Okay. Okay. Next, let's move on to the multi-tuning GUI. Uh, let's talk control loop first. Okay. The session covers a few control loops like current loop, speed loop, and the observer, and that time conversation. Okay. Let's review the multi-loop control architecture. The control rules refer to the PI controller inside the speed controller here, and the QS is current controller, and DSS current controller. Okay, and as well as the parameters of the observer here. Okay, so let's take a look at this current controller. Okay, let's check this diagram. This is basically a classic PI controller with saturation. This is a traditional PI controller, and with saturation limits added here. Okay, and in this page, in current controller, we use a algorithm based on frequency response to turn the current controller by setting the cutoff frequencies. Here, omega c. This is a cutoff frequencies. Okay. After input the omega c, the frequencies, this tool automatically calculate the PI controller parameters. Okay, and okay, the system automatically calculates the recommended parameters for both QSS KP and KI and the DSS KP and KI to a user. Okay, and then the saturation value um, we don't need to modify it. Okay, in the speed loop controller. Okay, so the tuning relies on user experience because in this system, we don't know the motor's load and the motor's condition. So it relies on user experience. Okay. But there is a very important parameter here is output max here. The number 3, output max. Okay. Let's check this speed loop output. This is a saturation limit parameters. Okay. So basically the maximum QSS current here, this place. Okay. If the load is too heavy, and the motor can't reach the target speed, you can try increasing this value. Okay, so this number is a value. Okay, so the load is too heavy. It means you have to increase torque. Increasing torque is equal to increase output maximum current IQ. Okay. Uh, okay, let me explain the sensorless module. This is a sensorless module. Okay. Uh, we use a back EF base series PLL estimation observer. So these observers parameters are mostly calculated from the motor parameters. So in previous tab, the motor parameters, we already input some motor parameters such as uh, inductance and resistance. Okay, and for uh, but what okay, but the observer parameters are automatically calculated by tools. So we don't need to tune the three parameters. Okay. But the PLL, the frost phase lock loop, we have to tune the parameters by users. Okay, but a good news is for similar application scenarios, the PLL parameters usually don't require much tuning. Okay, and to add the back EF estimated by the observer goes through the PLL. This is a PLL loop. Okay, and the observer goes through the PLL to obtain the rotor speed here, rotor speed. And the rotor speed, we also use a low pass filter to filter the signal. Okay, and by integrating the rotor speed, we also can get rotor position. Okay. The next part is the time compensation. Let's take a look at dead time compensation. In P-down control, dead time is added to prevent the upper and the lower switches from conducting at the same time. We call it short circuit. And however, this dead time causes distortion in the motor phase current. So, which can lead to, uh, okay, the motor phase current distortion, which can lead to a mechanical noise. So that's why we need a dead-time compensation algorithm. Okay. In the left graph shows the current waveform without compensation. Okay, so you can see some distortion on this current waveform. And the right graph shows it with compensation. Waveform has much less harmonic distortion. Uh, I think we can find it obviously. The waveform is better and it has lower total distortion. Okay, and the list parameters users don't need to tune it. We just use the typical value. Okay. To finish up the parameter overview, let's dive into the direction-aware motor startup feature in the motor tuning GUI. Okay. Actually, this part is more complicated. Okay. First, let's take a look at long trans state. Okay. In this section, after the motor starts running, and the D. Okay. On this slide, we just talked about in previous slide, and I just want to mention this state. We control this SS current and the Q SS current to 0. And why we need this state to we why do we need to use this state to stable the motor? Okay. Okay. I describe this this function. This helps stabilize both the controller and the observer in this state. Okay, so you can see this clearly in the waveform. The current is very small, and after trans state, we the state machine switch to closed loop. So you can see the current is increasing. Okay. Uh, okay. Next, let's move on to the headwind startup session. Okay. So this part is relatively more complicated. Since some fan applications have higher requirements for starting against headwind, so in this solution, uh, we have designed multiple combinations of headwind braking methods. Okay, so let's take a look at the first reverse startup scenario here. Okay, in the waveform, I describe this waveform first. The yellow trace shows the phase voltage, and the blue trace shows the phase current. Okay, at first, the fan is spinning here because of incoming air or wind. So which generates BKF. So we can see BKF waveform here. Okay, and once here, once the stop command is received in this moment, the motor enters. Okay, uh, we uh, we detect this state is on headwind state. So the motor enters the reverse closed loop state because the speed is higher. So we have to use reverse closed loop reverse to brake the motor. Okay, so in this mode, reverse mode, the motor uses closed loop control to brake the fan smoothly. Okay, the reason is we want to avoid large inrush currents thanks to current regulation. Okay, and after the speed drops to lower speed area, the motor switch to the brake here, brake state. Brake state where it's a three-phase short is applied to stop the rotor. So you can see that because it's a three-phase short, so the current is very huge. Okay, so finally the system proceeds to the uh, normal startup, a deep ramp up, and a closed loop. Okay, this is a first headwind startup scenario. Okay, now let's look at the second reverse startup scenario. Okay, in this method, we replace the brake state here. Replace the brake state with reverse ramp. Okay, reverse ramp is different from reverse. Okay, reverse function is running at closed loop, and the reverse ramp is running at open loop. Okay, and since the brake method involves a three-phase short, so it's a rather abrupt way to stop the motor. So if a more controlled and uh, gradual speed reduction is required, we recommend using reverse ramp to instead. So this approach allows the controller to slow down the motor more smoothly before transitioning to the normal startup. So you can see this current we use brake function to stop the motor. So the current is very big and slightly change. But in the headwind stop too, we use reverse ramp to stop the motor. So the code waveform is slowed down smoothly. Okay. Okay. Uh, let's take a look at this flow chart to understand how reverse startup works. So the items in green, the green words, okay, are the tunnable parameters in the GUI. Okay, like speed detect minima or maxima and the reverse speed threshold. Okay, okay, let's describe this flow chart. Step one, uh, the backhave detect state. First, okay, we use speed detect minima to check whether the motor has come to a stop. If uh, if the detected speed is higher than speed or lower than speed detect minima, it means this motor is uh is stopping. So the system goes to stop state. Okay. And the second, we check the speed. Uh, is it bigger than speed detect max? Okay. Uh, because we use it to is considered invalid condition. It's unreasonable speed. So uh, the detection will restart again. Okay. Okay. Next, we check the speed against. So the reverse speed threshold. Okay. Oh, here, which I just mentioned that reverse state is a closed loop braking control. Okay. So if the detecting speed is higher than reverse speed threshold, it means the speed is higher. So uh, we want to avoid circuit the circuit is broke down. So we use the reverse state to control and limit the current to brake the motor. Okay. Okay. If the detecting speed is lower, so we can use the brake function, brake state to stop the motor. Okay. And in the brake mode, there are two conditions for existing. Okay, first condition is speed is lower than quick speed, or the brake time the brake time is or is the brake time is retrieved brake time out. Okay. Okay. So for most parameters, we because I think this function is more difficult, and in some application, usually we don't need to use reverse function. Okay, so for most parameters, I recommend using the typical values are provided in GUI, like this typical value from the speed detect minima and the speed detect maxima initial duty and the reverse speed threshold. Okay, and users have to so this allows users to main focus on tuning reverse current. Okay. reverse current ID here and the reverse current IQ, the two parameters is a very crucial parameters in reverse state. Okay, so in general, the stronger reverse wind, it means the load is bigger. So we have to use higher IQ braking current here. Okay, and uh, typically we can set ID this number ID to 1 to 2 times the value of IQ. Okay, and the next part is brake. Okay, the brake session previously discussed applies a three-phase short circuit braking method. So it involves two key parameters here: maximum braking time and brake assist speed threshold. Okay, and this is a reverse ramp state. Okay. Oh, I mentioned again, the reverse ramp state operates in open loop mode. So where the brake current level requires careful attention here. This number, current comment. Okay. So I just mentioned that if the wind is strong, so uh, we have to properly increase the current command to brake the motor. Okay, the next tab is a note. Okay, this note is just a notebook feature. Use a record. Okay, to record important messages during development. Okay, so like the date and the customer name, or project name, or product name, and engineer name, etc. Okay, so note is the last line of the motor tuning GUI. Okay, and next, next is uh, okay. Previous slide we focus on motor tuning, but we also have to explain some firmware structure in KOC NTK. So in this slide, let's explain the project dictionary structure in the KOC development environment. Okay. Okay. In this diagram, it includes like here, BSP drive and the whole light system and start from the ARM ecosystem. This is the ARM ecosystem. Okay, is from ARM ecosystem. Okay, and all motor driver related files are placed on in app header and app source and user folders. Okay, and uh, we list some details, subroutines in this table. So if after this training course, you can check more uh, description in this table. And I just want to mention the important file. This file is nc parameter m0 dot h. This is a header file. It's generated from GUI tool. So okay. Finally, there is a RTT debug here. This is a RTT debug module, which functions like a PC a scope for monitoring program variables. Okay. And I just mentioned that more details can be found in the table on the right, and the users also can find more details in the example project file. Okay, and in the project structure, the main parts include some parts. Okay, I describe the important part. First is ADC IRQ handler. Okay, this handler is ADC conversion interrupts here. Okay, synchronized with the this interrupt synchronized with the PWM frequency and the core FOC control algorithm. The name is FOC main loop. This function uh, runs here. Okay, so you can see this FOC main loop. We just mentioned some phrase like uh, soft stop and pre-charge align ramp adapt ramp. So all motor state machine uh, is written here. Okay, and the next part is system tick IRQ handler. Uh, this handler is built-in is a built-in timer of the ARM Cortex N0. Is used as a divide. We use it as a divider for the main loop timing. Okay, the next part is main loop. The main loop. Uh, I highlight this function, task scheduler. Okay, so task scheduler to manage system functions and protection features. You can see here protection features, OVP, OCP, and timeout. And you can also see some speed loop control and motor retry function here. Okay. So for detailed functions, please refer to the diagram on here. Okay. And okay, there are some functions used for secondary development for user, implemented and configured through code. Okay, we have to program and we have to code it in the project. Okay, and most functions placed in a user here, user app and sub the .h. This file contains 4 parts. Okay, the include okay, first motor retry. Okay, wait a moment. Okay, motor retry defines the number of restart attempts after a protection event occurs and allows setting the interval time between restarts. Okay, and the second is interface setting. Okay, we usually use VSP or PWM to control this system. And and the third part is control mode. But now we just release speed loop. We don't release power loop, so we just can use speed loop now. Okay, and the F3 function. F3 function is a tachometer output interface, so where you can set how many pulses are generated per electrical cycle. Okay, so the parameters you have to input in this header file like this window. Okay, so defines the motor retry function. Okay, so there are 2 parameters you can input. First is retry times, is restart counts after an error, and and the retry delay time. So it's a delay between each retry attempt. Let's see this tip. Retry times equal to 255. It means retry uh, in indefinitely. Okay, and the second part is common control interfaces are divided into VSP level control and the PWM duty cycle control. We just mentioned this photo in previous page. Okay, uh, so VSP interface, so the configuration logic for both PWM and the VSP interfaces is the same, including setting for start value and the start value and the running value, start value and the max value. So, okay. Okay, the power control feature is currently not in use and has not been enabled yet. So let's skip this slide. Okay, F3 function. Uh, I just mentioned that F3 function is a tachometer output interface. So where you can set how many pulses are generated per electrical cycle. So there are two parameters to have to input. First is function enable or disable, and and you have to input the motor, the pole pairs of motor. Okay, and this example is the motor has five pole pairs. So you can see when I input the F3 gain is 5, you can check this equation. 5 divided 5 are equal to 1. So it means one pulse per electrical cycle. So uh, another example here, we input the gain is 10. So you can see uh, there are 2 pulse per electrical cycle. Okay, uh, let's introduce the evaluation board. Also, this is a PM 30003V 0405 IC evaluation board. Okay. In For this board is a low voltage application evaluation board. Okay. So you can see DC input, and this is a all-in-one controller. And we also provide a VSP controller, and shunt resistor here is for current sensing, and the J-Link connected port, it is used for programming and debugging. And here is UVW connectors. We use this port to connect motor. And here we also provide a function port. It's here there are some standard interfaces, PWM input and FG tachometer output. The next part, JScope is a debug tool released by Sega. This, okay. Commonly used for debugging and data monitoring. The program also includes a built-in RTT mode module. So you can find this module in the KOC in the project in KOC system.
Okay, that wraps up my training for today. Thank you for joining us. If you have any questions, feel free to contact your local sales, and make sure to follow PANJIT on LinkedIn to stay up to date with the latest news.